Right. So I have started the recording. You can write your roll numbers in the chat box. Right. So I guess how many participants? 29. 29. Okay, that's fine. So let's begin. Yesterday we have discussed coordinate system. In that first type of coordinate system is rectangular coordinate system, right? So today, yeah. So today we will discuss about cylindrical coordinate system. Cylindrical coordinate system, right? So they are just kind of like as their name implies, rectangular means kind of rectangular structure we have, and we specify a particular point in a free space with respect to that rectangular graphics, right? Here also we have this cylindrical coordinate system, right? In cylindrical coordinate system we can easily imagine that we have a kind of cylindrical structure, right? So this is what cylinder is, right? And inside this cylinder, suppose if you are having some point, right, which is placed over here. So this point will be defined with respect to this cylinder, right? So this is what the geometry and this is what the coordinate system is. Let us understand what are different points, what are different things involved in this cylindrical coordinate system, right? So I hope you understand the uh, overall picture. Now let us understand exactly what exactly it is. So let me draw XYZ axis first. So this is your Z axis, vertical axis. Am I audible? Is it visible?
Yes, sir. Yes, sir.
So this horizontal axis is y-axis. This axis is your x-axis, right? So x, y, z axis are there. After that, you have a cylinder like this. But before that, let me, okay, draw this way. This is one of the cutting edge of cylinder. This is another edge. And here it intersect with z-axis. Can I draw semi-sphere? No. Okay, fine. I'll try to draw. See, so this is the cylinder. Just a minute. Right. This is a kind of a slice of that cylinder. You can imagine, right? 1/4 part of the cylinder which I have just now here. I just have drawn one cylinder over here, right? So this is 1/4 part of that. Now, as I said, here it would be a x-axis. This is your y-axis, and this is the z-axis, right? Vertical axis is z-axis. Now I want to define a point which is present on this cylinder. Let's say somewhere here. with respect to that cylinder, and hence we are calling it as a cylindrical coordinate system. So let's say the point P is present here. This is point P, right? So this is point P. And when I say point P in cylindrical coordinate system, it is defined with respect to three parameters, and those three parameters are like R, comma, phi, comma, Z. These are the three parameters. These are the three coordinates by using which any point in cylindrical coordinate system can be defined. Right? Now, what do you mean by R? R is nothing but a radius measured from z-axis. So this is what your R. So this is R, radius measured from z-axis, right? Of course, it would be on a center point, but we have to measure it from z-axis. Remember that in cylindrical coordinate system, the radius is measured from z-axis, not from origin. So somebody may ask you, what is the difference between this radius from origin and radius from z? If you compare, radius from z would be lesser than radius from origin. So in case of cylindrical coordinate system, the radius is measured from z-axis. Keep it in mind. The next one we have is phi. Phi is the angle measured from, see, if you see this plane, like this plane is going to be your xy plane, right? Sorry. Which plane it is? XZ plane, right? So this is your XZ plane, and the angle made by this radius from XYZ plane, this angle is nothing but your phi. This is angle phi. Any doubt so far? Have you understood what is R? What is phi? Can someone respond if you have understood? R is the radius measured from z-axis. Phi is the angle between xy plane and the radius. Any doubt so far?
No, sir.
Okay. Then last parameter remaining here is Z. So this is your Z. Z is nothing but height of that point from zero or ground plane, right? So this is nothing but Z. This parameter is nothing but Z. So you got R, phi, and Z. And with respect to R, phi, Z, you can define any point on cylindrical coordinate system. Right? Is it clear? The next is unit vectors, like similar to the unit vectors that we have seen in a rectangular coordinate system, that is a bar x, a bar y, a bar z. Similar to that, we have unit vectors for cylindrical coordinate system also. And for cylindrical coordinate system, we have unit vectors like a bar r, a bar phi, and a bar z. Right? So how you can draw those unit vectors here? So let me draw unit vectors. This is your unit vector a bar r. Of course, it would be in the direction of r only. Then this would be your unit vector a bar z. This, of course, this would be in z direction, and this is unit vector a bar phi. I hope you understand the direction is same. Now let me write here. This is unit vector a bar r. This is unit vector a bar phi, and this is unit vector a bar z. Right? So with reference to that, let us define different characteristics for this cylindrical coordinate system. Right? Now for cylindrical coordinate system, we have the points. I'm writing the characteristics now. Number one. So of course, this is going to be a second type of coordinate system. In that, number one, point. So yesterday it was XYZ. Now here it is R, phi, Z. These are the points. Then we have unit vectors. Right? For the case of cylindrical coordinate system, what are the unit vectors? Unit vectors are A bar R, yes.
R, A bar phi, A bar Z.
Correct, absolutely correct. The next parameter that we have here is differential length. Differential lengths. So yesterday it was like dx, dy, dz. Here it will be dr, then differential length dr, comma r d phi. This is second differential length, and third one is dz. Right? Then we have differential surfaces. Differential surfaces, or you can say differential areas or area. Right? Now, as I said yesterday, the direction is given by third vector, whereas the multiplication of 2 will give you the area. Right? So here it would be of three types: ds bar when r is constant, then we have ds bar when phi is constant, then we have ds bar when z is constant. Right? So we have three different differential surfaces. Now, if r is constant, means the direction would be given by a bar r, right? So here I can write d r d phi dz, and the direction is given by a bar r. This is when r is constant. The next we can have phi constant, right? If phi is constant, then differential surface would be dr dz, right? And the direction is given by a bar phi, where this phi is constant. Phi is constant. Similarly, you can keep z constant. In that case, r dr d phi. This would be the surface. Direction is given by a bar z, and this is the case in which z is constant. I hope you understand what I have written here. Right? The next is differential volume. Differential volume. So how you write differential volume? You simply have to multiply all the differential lengths. So differential volume dV is equal to, you simply have to multiply all the differential lengths. So r dr d phi dz. So this is your differential volume. Got it? Have you understood? In the same fashion we have written it yesterday. Today also we are doing the same, just by changing the notations. I give you 2 minutes time to note it down. Quickly take a note of these points, because this differential length, differential surface, these are all required for solving the examples based on electromagnetics. So knowledge of differential length and knowledge of differential surfaces is very important with respect to different coordinate systems. So yesterday I have given you differential length and differential surfaces for rectangular coordinate system, and today it is mentioned here for it is mentioned for cylindrical coordinate system. So please take a note of this quickly. Copied this? Can anyone respond?
Yes, sir.
Okay. So one student, if he or she can copy, then that is like assumption. Everyone can copy. So if one student have completed, that means the time given for copying is sufficient. So that means I can proceed further. Now it's up to you whether to copy it or whether to just say that copied or not, right? Because to be frank, I can say here we don't have the control. We don't. In fact, we lost the control of your academics, like what to write and whether you are really writing in the notebook or not, right? So with just a hope that whatever instruction we pass on in the class, you will follow all the instructions. With that hope only, we are proceeding further, right? So let's move on with the third type, that is spherical coordinate system. Please note it. Third type is spherical coordinate system. Third type, spherical coordinate system. Right? So spherical coordinate system. Now, in case of rectangular, as I said, there would be a rectangular block, and uh, the this point is defined with respect to that rectangle. In case of cylindrical coordinate system, as I said, there would be an cylinder, and the point inside that would be defined with respect to the cylinder. Now, as its name implies, spherical coordinate system, there would be a sphere, and the point inside that would be defined with respect to that sphere, right? So let us move ahead to understand what is there in spherical coordinate system, right? So if I can draw this like okay, suppose you are you are having a watermelon. If you are having a spherical shaped watermelon, right? Then if you try to cut this in three different ways, like suppose if you have a slice on let's say xy plane, yz plane, and xz plane. So if you could uh, apply the knife on this watermelon in those three directions, you will find this watermelon will be cut into the pieces. You will find out that there is one piece coming out, and if you remove that single piece, After applying knife from those three directions, you will find this type of uh, uh, a cross section on that watermelon, right? So this geometry I will try to draw. So this is your x-axis, this is y-axis, and this is z-axis. I hope you understand. You are applying knife from those three planes, like xy plane, yz plane, and xz plane. If you take cut on this watermelon, a piece will come out, and this would be the geometry. You will be able to find those three axes inside it: x-axis, y-axis, and z-axis. Can you imagine that? So let's move ahead. So let me draw here. This is your z-axis. This would be a y-axis, and this is the x-axis, right? So let me write. This is x-axis, y-axis, and z-axis. Right now, I want to draw this cross section of that watermelon here, right? So if I could draw this, it will look like this. This would be the section of watermelon on xz plane. Right. So this would be the cross section of watermelon on yz plane, and this is the cross section of watermelon on xy plane, right? So that's all. This is your spherical coordinate system. Now let us try to understand how the point is defined in this spherical coordinate system, right? So let me draw the point somewhere here. So this is your point P. This is point P. This is point P, right? And let me tell you, the point P is defined with respect to three coordinates again, here also in spherical coordinate system, and the coordinates are, or the point is defined with respect to coordinates which are r, then theta, then phi, right? So most of the things you are aware already. You know r, you know phi, right? So but here in this case, my meaning of r is different. Let us understand how it is different, but before that, keep it in mind: rectangular coordinate system xyz, cylindrical coordinate system r theta phi, sorry, r phi z, and for spherical coordinates we have this r theta phi. Now let us understand what is r, what is theta, and what is phi. I can easily identify whomever is doing no. I can easily identify because the recording is going on. Roll number 40. Roll number 40. Roll number 40 is there. Roll number 40. Can you respond?
डबल पण अडवत होती बरं का अडवलं असतं डबल.
Roll number 40. Can you respond? Can you hear me? Sagar Patil. Sagar Patil, I am not able to clean the screen. Do you understand what I said? Sagar Patil, are you able to hear me? Okay. Got it. We can. No problem. Sagar Patil, if you are busy, you can leave the class. Sagar Patil, you don't have to unmute. You can leave the class if you have some work. Okay, I guess he left the meeting. Okay, fine. So others, this could be a learning lesson. If you are not attending, if you are outside, if you are outside, in that case, you should not join the class. It will be creating unnecessarily disturbance. Maybe he was outside and he was attending the class, and I guess by mistake he turned on the screen, log into the screen. So that's why this has happened. Okay, let it be. He will call me afterwards once I put his absenteeism. We have R, theta, phi. Can someone respond? Is it visible?
Yes, sir, visible.
Okay, now we are trying to understand what is R. R means it's a distance measured from origin. This is your radius R. Try to understand the difference between the radius which we have drawn for cylindrical coordinate system and the one which I have drawn just now for spherical coordinate system. So this is your radius R. In case of cylindrical coordinate system, the radius is drawn from z-axis. And in case of spherical coordinate system, the radius is drawn from origin. Radius is drawn from origin. So whenever we talk about radius of spherical coordinate system, it would be always greater than radius that you find in a cylindrical coordinate system. Radius of spherical coordinate system is always greater than radius of cylindrical coordinate system, right? So with the help of formula also I can prove you this, but still keep it in mind, radius measured from origin. This is for spherical coordinate system, right? Next is theta, right? So what is this theta? So you have to draw the shadow of this radius. You have to draw the shadow of this radius. So let me draw the shadow of this radius here. I hope it's visible. So this is the shadow of this radius. Can you imagine this is your radius, and if I plot the shadow of this radius, it would be on a xy plane. It would look like this. So I have plotted the shadow of that radius. Now I'm going to draw the two parameters called as theta and phi. Now theta is the angle made by z-axis with radius. Theta is the angle made by z-axis with radius. So this is the theta. This is theta. And phi is the angle made by x-axis with the shadow of radius. So this is the phi. Are you getting? Theta is the angle made by z-axis with radius, and phi is the angle made by x-axis with shadow of radius. This is the shadow of radius, right? Or you can say this phi is the angle made by xz plane with radius. In other words, I can say phi is the angle made by xz plane with radius. Right? Is that clear? So value of phi, it would be same for its cylindrical coordinate system and spherical coordinate system. Right? So with that note, let me move ahead for unit vectors. Now here also we have some unit vectors. So those unit vectors would be a bar r, that would be in the direction of radius. So this is a bar r. Then we have a bar theta, that a bar theta would be in the direction of theta. So this would be the a bar theta. And a bar phi, this is in the direction of phi. Right? So we have those three unit vectors. One, it's in a direction of a bar r, a bar r. So this is your a bar phi, and this is your a bar r. Sorry, this is your a bar theta. Right? So let's understand. Let us write different characteristics involved in this. So characteristics of a spherical coordinate system. The first characteristic, the point. So point is defined with respect to three coordinates. So point, if I say point P, it will have three coordinates r, theta, phi. Then we have second characteristic, it would be unit vectors. What are all unit vectors? It would be a bar r, a bar theta, a bar phi. Then similarly, we have next point is differential length. So differential length, we have here differential lengths as dr, comma, r d theta, comma, r sin theta d phi, r sin theta d phi. See, these are differential lengths of spherical coordinate system. Then we have differential areas, differential surface or differential areas. Right, here also you have three differential areas. First one by keeping r constant. Next one is by keeping theta constant, sorry, phi constant. Yeah, theta constant. And last one is by keeping phi constant. Right. So first of all, let us keep r constant. Direction would be given by a bar r. So remaining terms, you can take it as a multiplication of those terms. So here it would be r into r. So r square sine theta d theta d phi. Now this direction is given by a bar r because we have kept r as a constant. So this is for the case when r is constant, radius is constant. Next we have ds bar for theta constant, right? So when this theta is constant, you simply have to multiply this length and this length. So r dr sine theta, r dr sine theta d phi, and the direction is given by theta. So a bar theta, right? So this is the case where theta is constant. And last case is by considering this phi constant, right? So this would be r dr d theta, direction is given by a bar phi, and we know that this is for phi is constant, right? So these are all characteristic. What about differential volume? Simply multiply all the lengths. Differential volume. So here you can write dv. dv is equal to r square dr d theta sorry, before that sine theta is to be written. So r square dr sine theta d theta d phi. So this is the volume, differential volume for spherical coordinate system. So please take a note of these points. Very, very important to solve examples. Just a minute. Hello. Hello. Yes, ma'am. Tell me. No, no, they will not appear at 130. They will directly appear at 230. Yes. Right. Have you noted this, everyone?
Yes, sir.
Okay. Okay. Now, next point, which is very, very important. Let me save this. Relation between different coordinate system. Now, to begin with, let's start with relationship, or you can say comparison between different coordinate systems, right? So for that, I will write heading here: relation between Cartesian coordinate system and spherical coordinates, cylindrical coordinate system. So many of the times, even though the examination is conducted online or offline, MCQs are being asked on this concept only. If you know those relationship, then only you will be able to find out the answer. So this is a relation. Just a relation between Cartesian or rectangular and cylindrical coordinate system. See, there is a proof to derive those relationship, but I want to keep it simplified. If the things are online, there would not be a need of that proof. If um, the examination would be conducted offline, if students would start onboarding, I will discuss the proof in class itself. But as of now, it's not a part of syllabus, but still we should know the relationship between those coordinate system, right? So first thing, if I want to convert, if the point is given in cylindrical coordinate system, and if you want to convert that point into a rectangular coordinate system, then what relations you can use. So simply here I can write cylindrical coordinates are known. Means what? Which coordinates are known to you? You have r, then you have phi, and you have z. If you know those coordinates, how you can convert it into a rectangular coordinate system? You know that rectangular coordinate system must consist of x, y, and z. Means what? Point is represented in terms of r, phi, and z. Now you have to convert it into x, y, z. So what relations you will be using is, first, number one, it is x is equal to r cos phi. This is the first relation. Second relation, to find y is equal to r sin phi. And last one is nothing but your z. Z is equal to z in both the cases. Z is equal to z. So I hope you will take a note of this. These are very, very important relation to convert the point from cylindrical coordinate system to rectangular coordinate system. This is case one. I can derive the relation. I can derive those relations. I can show you the proof of those relations, but whenever it is required, at this point of time, it's not required. I can prove this, right? I can prove those relationships with respect to some assumptions, but if it is required, I'll do that, right? At this point of time, we require only the relationships. So this is the relation by using which you can convert the given point which is specified in cylindrical to rectangular coordinate system, and vice versa is also possible if the point is specified in rectangular coordinate system. If rectangular coordinate system is used to specify the point, and we know that it's x, y, and z. The point would be specified with respect to x, y, z, and I want to convert that point into cylindrical coordinate system, right? If I want to convert in a cylindrical coordinate system, then I have to find those parameters like r, phi, and z. So what are the relations? What are the equations to convert this x, y, z into r, phi, z? So to convert that, let me write some expressions here. R is equal to under root x square plus y square. X square plus y square. This is the relation. So if you know xy, you can find r. If you know the value of x and y, you can find out r. Then similar to that, we have expression for phi. Phi is equal to tan inverse of y by x. Tan inverse of y by x. So if you know the value of y, if you know the value of x, you can easily find out the value of phi. And similarly, for z, we can write z is same for both the cases. So here I can highlight this thing. Right? Any doubts so far? Many of you might have seen those expressions, relations earlier. Just to recall, just to remember, uh, if you want, you can take a note of this. Shall I proceed further?
Yes, sir.
Okay. Right, next is relation between rectangular coordinate system and spherical coordinate system. So let me clear this cylindrical. Yes. And here I'm trying to write the relation between rectangular coordinate system and spherical coordinate system. So I will use the same screen, and here I will write a spherical coordinate system. So first case, I want to convert a spherical to rectangle, and in case of spherical, we know that the point is defined with respect to r, theta, and phi. R, theta, and phi. So if the point is defined with respect to r, theta, phi, and if you want to convert it into x, y, z, we have another set of equations where x is equal to r sine theta cos phi. R sine theta cos phi. Then we have equation for y is equal to r sine theta sine phi. R sine theta sine phi. And we have relation for z. Z is equal to, now here in this case, z will not be same for both the cases. So z is equal to r cos theta. Z is equal to r cos theta. So those are three relations, three equations by using which you can convert a given point into rectangular coordinate system. Right? Now next, we have another set of equations to convert rectangular coordinate system into spherical coordinate system. So in spherical coordinate system, we need to identify, we need to find r, theta, and phi. and we have three equations. For r, we have equation which is equal to under root r square plus, sorry, this has to be x square plus y square plus z square. See, if you compare this relation of r for cylindrical coordinate system, it was under root x square plus y square. Just now I told you. Here in this case, it is x square under root x square plus y square plus z square. Of course, for this case, the value would be high because we have added this term here. Z square would be added. So that means radius of spherical coordinate system is always greater than radius of cylindrical coordinate system. This is basic concept. Then we have theta. Value of theta is equal to cos inverse of under root z upon under root x square plus y square plus z square, which is basically a value of r. If you have already calculated the value of r, you can simply consider this as cos inverse z by r. Then next you can find phi. Value of phi is equal to tan inverse of y by x. As I said, the value of phi for cylindrical coordinate system and value of phi for spherical coordinate system, it would be same for both the coordinate systems, right? So let me highlight once again. This is r, this is phi, sorry, theta, and this is phi. So I hope you understand the relations. Tomorrow we will solve some of the examples based on this concept. And as far as first unit is concerned, it's almost done. So most probably in the next lecture, we will start with the second chapter, that is electrostatic field. Right. So tomorrow we will solve some of the examples based on the concept that we have studied today. And just a minute. So tomorrow we will solve some examples, and then we will start with second unit. Now, if you have any doubt, you can ask. If no doubt, you can write your roll numbers in the chat box. I will stop screen sharing. You can write your roll numbers in the chat box. Let me take the attendance first. Then you are allowed to leave the meeting. Yes, roll number 1. Roll number 2. 4. 12. Roll number 12. 18. Roll number 18. 29. Roll number 29. 32. Roll number 32. 36. Roll number 36. Roll number 38. 38. 40. Roll number 40. 41. Roll number 45. 46. 47, 48. Okay, fine. You are allowed to leave the meeting now.
Sir,
Yes.
roll number 19.
Roll number.
19.
You are present, not an issue.
Sir, 33.
No, I just took the numbers of absent numbers. Others are present.
Okay, sir.